Good afternoon, everyone, and welcome to the Construct and Innovate webinar series on sustainability planning and construction. My name is Jamie Goggins, and I'm co-director of Construct Innovate, which is Ireland's National Research Centre for Construction Technology and Innovation. This is a 7-part webinar series. This week, the concentration is on achieving high-quality indoor environmental conditions in buildings. So here the focus will be maybe a bit less on the technology, but in the terms of the requirements and why we need to achieve high-quality indoor environmental conditions. As I said, this is part of a 7-part series in there, and we're on week 4 of that 7-part series. We're really fortunate to have absolutely fantastic speakers, eminent people in the area to speak today. So our first speaker is Professor Paweł Wargocki, who's Professor at Technical University of Denmark, or DTU, and he's going to talk about indoor air quality. So Paweł is, it's a lot of research done on human requirements and indoor environmental conditions, and looking at what the impact is on indoor environmental conditions in terms of our productivity at work and our performance in terms of our learning and so on. Then we've got Simon Jones, who's founder of Air Quality Matters. So that's both a consultancy service, and he runs a really successful podcast. And he's going to talk about changing the framing of indoor air quality. So effectively, what he does, he translates that technical detail around indoor air quality, ventilation, retrofitting, and so on, all those strategies, and makes it more easy and accessible for us to understand in terms of the indoor air quality. Then we have Medeina Macenaite, who's a doctoral researcher at the University of Galway, and she's going to talk to us about a survey that they did as part of the BVent project, where they explored the human interaction with ventilation and indoor air quality, and that was done in Ireland. And then we have Dr. Eoin King, who's the director of the Galway Sound Lab based at the University of Galway, and he's going to talk about indoor soundscapes in there. So really excited speakers today, so really looking forward to this. So without further ado, I'm going to hand over to our first speaker. First speaker is Paweł. So over to you, Paweł.
I was introduced already, so I'm professor at the Technical University of Denmark, and I was asked to give you a short course on the indoor air quality. I have 15 minutes. So I'll guide you from what is the indoor air quality, what are the major challenges. The 15 minutes is, of course, not enough. And if you have any questions that I am not able to address and we will be not able to address in the question and answer session, you are always welcome to drop me a mail afterwards. So let's start with saying that basically when we are talking about indoor air quality, we have to talk about the overall indoor environmental quality in buildings. So when we talk about the buildings, we need to understand that the indoor air quality is an element or component of the overall indoor environmental quality and plays important role in establishing the environment that is good for our health, comfort, productivity, sleep, learning, and so on and so on. The other parameters are thermal, light, and acoustic that I will not speak about. There is some interaction between those. We have very little information about this as well. Recently, we also speak about 2 other aspects of indoor environmental quality that are important. It's the human behavior. It is providing people with opportunities to adjust the conditions in buildings according to their preferences and needs, and then biophilic design that is allowing us to contact with nature and also having a lot of daylight. So what is the universe of indoor air quality? If we want to define indoor air quality, we could define it as a mixture of gaseous pollutants, particulate matter, and biological agents. And among gaseous pollutants, we have organic, inorganic pollutants and radon. Particulate matter, these were fibers, organic, mineral, and metallic, and then biological agents, that would be allergens, mold, fungi, and of course, viruses and bacteria. In some definitions, actually refer to the indoor air quality as the aspects of thermal and relative humidity. But basically, originally, I would not include them as in the definition of indoor air quality, although both of them impact some of the elements that are, or some of the elements that are in the universe of indoor air quality. The sources of indoor air pollutants include outdoor air, building itself, then ventilation systems and humans. And it's very important here that we understand that everything that is in the building can affect the pollution in the building, so indoor air. But sometimes we forget about the outdoor air. So our buildings, despite that they are very tight, some of them, at least those new that are energy retrofitted, there will be always transport of the outdoor air pollutants in the outdoor air to indoors. So we cannot forget about that. Outdoor air is a significant component of the universe of pollutants in indoor air, and then can actually influence how the quality is perceived indoors. One other aspect that we forget about when we talk about indoor air quality is the chemical transformation. So we have a primary sources of emission, and those primary sources could be, for example, transport of the pollutants, emissions from building materials, emissions from the systems, technical systems in a building, and then emissions from humans. But also we have so-called secondary emissions, or I would say products of indoor air chemistry. So similarly to what is happening outdoors, indoor air is not static, it's very dynamic, and that there are processes occurring through the chemical transformations and the presence of oxidative species that transform the pollutants that are primarily emitted from sources to another pollutants. Sometimes those are more toxic than the precursors of that. So what we know about indoor air pollution and indoor air quality? We know very little, to be honest. New chemicals and other contaminants appear in buildings almost daily. Many in the indoor air community fear that some of these may be significant health hazard, and certainly they will be. And there could be also contaminants of concern that are yet not identified, but they may have significant health effects. So among all the pollutants that are introduced, every day there are several hundred of new pollutants introduced, actually. Among those thousands of chemicals that are in commerce, only we know 1% for the toxicity. So we have little information, but it should not stop us from doing something. But I just want to tell you that the universe is very complicated. There are many pollutants. For many of those, we don't have little information. But for some, we know, and on those, we can, of course, act. Why we need to think about indoor air quality, and I think Simon Jones will speak about it more, because I provide you with some background information mainly, but basically our habitat. I mean, our previous habitat was outdoors, today is indoors. So we spend the time indoors. Of the 79 years of average life of a male in EU, the 69 years will be in buildings. Only 6 years out in outdoor air. Even if it is increased to 10 years, it still be a significant, even 12 years, the indoor will be a significant part of this. This is the first thing. The second thing is that if we think about how much we inhale the air compared to how much we drink, for example, so during the lifetime of 79 years, we breathe about 343 billion liters of air. It's about 11,000 liters a day, while we drink only 94,000 liters of water, about 2-3 liters a day. So you can see this is several orders of magnitude, much more, with potential consequences. And those consequences are the effects on work, on learning, and sleep. I don't have time to go through all those, but importantly, we have to see that we have seen recently in the research that also our sleep quality is disturbed by the poor air quality. And those disturbances actually are not meaningless. They are small. We are not talking about 10, 20, 30%. We are talking about a few percent, more for the children in schools than for adults in working environments. But if we look at those from the economic point of view, those effects are significant. So the economic implications of those effects are huge. And there is documentation that even modest gain in work performance can deliver significant financial benefits. So even if we measure 1% improved productivity, that will be a cost effective because of the split of costs in a building, where the 90% of the costs are actually attributed to work staff, and then the rest is for the other aspects of running the building. Payback times are usually less than 1, maximum 2 years. And if we sleep short, and we can lose a lot of working days. Not only that we perform less well, probably, but we also lose the work days because we are less able to perform our work. So how to improve indoor air quality? In order to improve indoor air quality, we need to understand our exposure. So our exposure. So basically, the exposure is modified by processes that are happening in the space. So the ventilation, infiltration, and the transport of pollutants from outside, and also various indoor sources that emit. So all those together, they define our exposure, which is the concentration of pollutants in the air that we inhale. And we can uptake those pollutants in two different ways. I don't have much time to talk about it, but mainly we inhale, but also we uptake through skin some of those pollutants. And this is not insignificant uptake, actually. For some pollutants, even 50-50 through the skin compared to the inhalation. And those affects health of comfort. So in order to improve indoor air quality, we should not only think about, let's say, emission from materials or outdoor sources of ventilation, but we need to think about exposure. It is the exposure that affects us, and not ventilation directly. Therefore, in order to improve the air quality, there are three major ways of doing it. Is a source control or the local exhaust. It's the ventilation, of course, or airing or diluting of pollutants, and then air cleaning and filtration as the last one. But before I say that, I think I want to say about the one air paradigm. The one air paradigm suggests that we should not create the artificial separation between outdoor and indoor air. Good indoor air requires that outdoor air is also of the high quality, and if it is not, everything has to be done to make sure that the air that is delivered indoors is of a high quality. Otherwise, all our efforts to improve indoor air quality will be, not that effective, I would say. They will be still effective, but not that effective because of the impact of outdoor air. So the source control is the most effective way. Sources dominate. There is a great diversity of sources, of products. So we need some standardization. And there has been some standardization at the EU level, which is the building material labeling through EU LCI concept, where there are 200 different pollutants and other directives such as REACH, for example. However, we don't have a clear connection about, say, how those pollutants, whether with these pollutants how can we define the emissions indoors? There are attempts at the EU to do that. The next is ventilation. This is rather complicated. This is how the ventilation requirements changed over the last 200 years. And you can see it can be high, it can be low, and so ventilation is not a given number. It is a given number by standards, but it is the result of a certain either political or economical or any agreement at the standardization level. It doesn't mean we should not use it, but it means that it actually depends on different aspects. And this is as I showed in the exposure. There could be a different way of looking at the ventilation requirements is to look through defining a base requirement and then provide an extra ventilation above base depending on the exposure. Then we could have the ventilation requirements for endemic and pandemic conditions, because it is very important that we also need to consider and prepare the buildings for the potential of the new pandemic or small epidemic. And then air cleaning. I think I see a lot of potential of air cleaning, but there is a limited data documenting the effectiveness of air cleaning. The most important is that we don't have a long-term performance of air cleaning, besides filtration, for which we have a lot. And then secondly, we have not standards, not very good standards for actually assessing the effectiveness of air cleaning. So how we measure indoor air quality? There could be two different ways of looking at measuring air quality: as a physical-chemical measurements using detection tubes, semiconductor sensors, and so on, so on. And then we can do also by asking people. People can evaluate acceptability of air quality, comfort, odor intensity, freshness, or actually report non-clinical health symptoms that basically can be related to the air quality conditions. Do we have a metric of indoor air quality? Because that would be the question. We actually don't have. The most typical metric that is used is the ventilation rate and carbon dioxide, and these are associated with the air quality, with all the pros and cons. So carbon dioxide, basically, it is the proxy indicator for ventilation rate. And ventilation rate is a proxy indicator for indoor air quality. But if we look at the exposure, then if the low emission, if we have buildings with low emissions, then ventilation rate doesn't have to be very high in order to achieve indoor air quality. So there are those pros and cons. In the past, total concentration of volatile organic compounds was used, and it is now promoted through low-cost sensors. However, we have no evidence that there is a connection to the responses of humans or outcomes of that metric, and this metric is defined differently from what has been proposed in the original definition of that metric. And then actually occupant complaints and acceptability, as I said, are subjective. Indoor air quality is actually invisible threat. So we can be exposed to the low levels today and have symptoms or health problems in 10 or 20 years ahead of us. I'll be finishing in a moment. So there is no formal agreement on pollutants for monitoring. There could be a way how we can look at this. By the way that I'm presenting here is to looking at those that are used today, CO2 and ventilation, and then those that are in the WHO air quality guidelines, such as NO2, benzene, PM2.5, formaldehyde, radon, and ozone. And we have to think about ozone not only from the effects of ozone, but also ozone participating in the chemical transformations and producing the harmful byproducts, as I said before. One important message is that at last, indoor environmental quality is a part of the Energy Performance of Building Directive of the recast. And although this is not explicitly indoor air quality, but the ventilation rates and presence of contaminants, this is actually a significant step forward, which will help us to regulate indoor air quality in buildings. But of course, we need an infection control that is not addressed so far in the documents, except for the standard 241 produced by the US. So what are the future challenges and opportunities? I believe that Simon will speak and develop, actually elaborate more on this. I think one important thing is the last dot I'm speaking now is a benchmarking and making invisible visible. We need to have an IAQ monitor. The public is not aware of the problems of IAQ because we cannot see the pollutants. Similarly, we could not see the viruses during the recent pandemic. So we need to have somehow, we need to make it visible, and we need to inform the public about the potential risks, but also about the potential benefits. So we need to think about IAQ as the supporting health, not only the diminishing risk, but also supporting health. So if from the point of salutogenetic design, and you can ask how to do it, we really don't know yet, but there are processes of the thinking has been started in that direction. And also I propose, and then maybe Simon will develop further, is a new definition of indoor air quality, which we think about, we talk about pollutant, but it's the resource benefiting healthy living. As we look at the water, exercise, walking, sleep, and so on, this is a resource that benefits our healthy living. So indoor air quality can also be considered as the resource benefiting healthy living. I hope that Simon will develop this further. So thank you very much for your attention. This is my email address. You can also check my LinkedIn profile and connect with me over there. Thanks a lot for your attention.
Brilliant. Thanks, Paweł. That's really, really great presentation, kind of setting the scene around indoor air quality and why we really need to take it seriously. I think that the new definition you talk about, that indoor air quality as a human as a resource benefit for human health, I think is a really important message. And even when you talk about the 1%, 2%, 3% maybe improvement, say in productivity, if I take 1% improvement in productivity in the workforce in a building, that actually can pay for the whole capital costs of the building over the life of the building. So there's a kind of very easy calculation you can do there. So every percent matters in that, and we really need to value, our workforce, value their health, and then that's productivity. Obviously, less sick days and happier people will make it for a happier company as well. So that's what that. So if anyone has any questions for Paweł, please put them in the Q&A function at the bottom of the screen and that, and then we'll deal with all the questions at the very end. So we're going to move over to our second speakers, over to Simon Jones, founder of Air Quality Matters, and he's going to build on some of the stuff that Paweł has talked about, and he's going to speak about changing the framing of indoor air quality. So over to you, Simon.
Thanks a million, and thanks, Paweł. I only have to throw out half of my slides, so I'll pivot. Only joking. So let me just share my screen here. If somebody could just give me the nod that that's working, I'd appreciate it.
Perfect.
Yeah, brilliant. Well, hello everybody. I'm going to kind of top and tail a little bit actually what Paweł's been talking about. As you can imagine, there's quite a bit of crossover, but really what I wanted to focus in on today is 3 or 4 principal things. One, some basic hard numbers behind this, which we'll have at the beginning, at the end, which you've seen in Paweł's presentation, but I think it's worth repeating. Apologies, there's now a delivery driver. My dog's going nuts, I think. The second thing is about agency and visibility, which again Paweł touched on a little bit, but I also want to talk about. I also want to talk about why this stuff matters and perhaps why we've been getting it wrong, and a little bit around a thought experiment to put this into context for people. Let's crack on and get through this. So as Paweł mentioned, there's some fundamental maths behind our buildings, and it dictates why this stuff is so important to us in the long term. If we live to 80 years of age, as Paweł mentioned, 70 years of our life approximately going to be spent indoors, 55 years of that at home. So our buildings, our homes, and where we're educated have a profound impact on our long-term health and well-being outcomes. The trouble is it's very hard for us to articulate, and you probably sense that listening to Paweł, what good air quality actually means. What is acceptable? How do we define that in plain English? And for normal consumers, how do we get our heads and wrap our heads around what good looks like? We've been listening to people talk about air quality for approximately 20 minutes at this stage, and not once has any of us taken a breath and thought objectively about what the quality of that air we were breathing was. If you were to take a jar and put a lid on it right now in the room that you were in and send it off to the lab, it'd be very difficult for you to guess what you'd find in that jar when it comes to air quality. And we don't get agency in this. When we're presented with choices in our built environment, whether it's a show home or homes that we're going to buy, whether it's an Airbnb we're going to rent, whether it's our own homes, it's very difficult to understand whether or not air quality is very good. We have to rely on our perception often of whether a place feels stuffy or there's odors that we find unpleasant. But beyond that, it's very difficult for us to know objectively whether the air is any good. Similarly, in a workplace, we can find that we can have choices of meeting spaces and objectively be given no choice as to what the air quality is likely to be in that space. We have to almost completely rely that the building HVAC system is doing what it's supposed to do. The room that you're in right now, is the air quality any good? Do you know? The trouble is this stuff really matters. The cost to human health and well-being is almost, not quite, but almost incalculable. If we just take one simple illness or disease that we know is significantly exacerbated by poor indoor environments, that's asthma. That condition alone affects nearly 5.5 million people in the UK. It's a disease that costs the US economy more than 80 billion a year annually. And it's estimated that somewhere between 30 and 50 million people in Europe, approximately 10% of all Europeans, are affected by asthma. And that costs the European economy nearly 20 billion per year. In Ireland, where I live and where we're talking to you today from, every 4.5 minutes, somebody in Ireland is admitted to hospital with asthma. So that disease alone has a huge impact on our long-term health and well-being and costs to the economy. Ventilation, something that we know is a significant pillar for good outcomes in the built environment, we don't get right nearly enough. A recent study in the UK found that 71% of homes across the entire building stock did not have the ventilation provisions that met current building regulations. That's not the performance, that's actually a missing component parts of a ventilation system in a building. Nearly 3/4 of all properties were missing some substantive part of a ventilation system. The last time this was looked at a European level, somewhere between 22 and 55% of all ventilation system flow rates were below regulations, and between 55 and 75% of users operated those systems at lower rates than they should be. Even in markets with more advanced ventilation economies, with balanced whole house heat recovery, 50% of those systems were found to be either out of balance or malfunctioning. So we get this wrong a lot. And why is that? Well, we haven't really thought about the impacts of indoor air quality on our health. It's not something that we think about day to day, minute to minute. And up until recently, it's been quite expensive to see the quality of the air that you're breathing. But that's fundamentally changing. The cost of sensors that can detect relatively simple air quality metrics are getting cheaper and cheaper. But fundamentally, we've assumed that because standards exist, that somehow the supply chain will deliver. And we've delivered ventilation mostly by specification of the product, not on performance. So if we think of our stock condition surveys and our social housing and even our own properties, we assume because a thing is there that it's doing what it should do. And every time we go and check this, we find that's very much not the case. So I just wanted to very quickly talk about a little thought experiment to just kind of demonstrate why this stuff's so important. Just imagine for a moment that every rooftop, every house, every workplace, every education building, every home had a fantastic ventilation system on the rooftop. And that ventilation system had super efficient filters on it, capturing all the pollutants, the particles, the chemicals, the viruses that might be floating around in the air, 24 hours a day, 7 days a week, 365 days a year. That would be a fantastic scenario, wouldn't it? Every single building that we sat in had a system on the roof that was perfectly filtering out all of the pollutants from the air that was being brought into those buildings. But there was a catch. Instead of these filters capturing pollutants, they passed them directly into the water systems of those buildings. 24 hours a day, 7 days a week, 365 days a year. That's just the way it is. That's just the way buildings work, and there's nothing you can do about it. Ventilation systems that sit on roofs capture all of the pollutants that might be there and pass it directly into the plumbing and the water systems of those buildings. That's the water that you drink, the food that you eat, and the water that you bathe in. 24 hours a day, 7 days a week, 365 days a year. You wash your food in it, you bathe your kids in it, they drink the water. There's nothing you can do about it. That's just the way it is. You'd be outraged, right? What could you do? There's only one thing you can do, and that is try and reduce the pollutants that are in the air. Now, there is a system like that in our built environment, and it's called us. And those systems are our lungs. 24 hours a day, 7 days a week, 365 days a year, from the day that you were born until the day that you die, that ventilation system for your body is on. And what we don't recognize is our lungs are incredibly efficient delivery systems for the pollutants that are in the air. If you think about an inhaler, that's a great way of getting medicine directly to the bloodstream and to the lungs where it's needed. It does that because it's an incredibly efficient delivery system. And what we now know is that the pollution in the air that we're breathing, affects every single organ of the body. We can now directly attribute air pollution and the pollutants in the air that we're breathing to early onset dementia and Alzheimer's, lung disease, cardiovascular disease, liver and kidney disease, cancer, low birth weights, endocrine disruption. The list goes on and on and on. Because the air that we're breathing, all of those pollutants are delivered very efficiently to every organ and cell of the body. You don't have a choice. That's just the way it is. So what do you do about it? We have to start reframing and thinking about the quality of the air that we're breathing. And if that's not enough to top and tail the conversation the same way Paweł did, there's a business case to this. There are hard numbers behind this as well. If you don't care about the air quality and your health, perhaps you'll care about the numbers. Paweł showed this number, but it's worth revisiting. There's an old real estate rule, and it's called the 330-300 rule. And that is for every $3 you spend on energy, you'll spend about $30 on rent. And for every $30 on rent that you spend, you'll spend about $300 on staff costs. And that's one of these truisms in the workplace that's stood the test of time. What this means in practice is that 90% of the costs to a business are buried in salaries and costs and wages. So we spend, if you think about it, an inordinate amount of money making our buildings more energy efficient and sustainable, as right we should. But the reality is that reflects only 1% of the costs to a business. 90% are still buried in staff costs and salaries and so on. So enhancements to ventilation, air filtration, and the control of indoor pollutants can lead to significant gains in productivity. We know this, and the evidence suggests somewhere around 10%. But even if we're massively conservative and say it's 2 or 3 or 4% gains in productivity to a workplace because of a good environment, at 90% of the cost to the business, that's a huge impact on that business, notwithstanding the impact on things like sick leave and increasingly absenteeism. And now we've made the workplace even more complex by having a hybrid environment where many people are working from home. And if you cast your mind back to the beginning of the presentation, 3/4 of the homes that we occupy are probably significantly underventilated. So there are people starting work today in their home office in the same room that they went to bed in last night. It probably wasn't well ventilated last night, and it probably isn't well ventilated today. So these things do have an impact on people. So just to finish the presentation off, we have to reframe how we think about air quality in our built environment. This stuff does impact us, it has a cost, and if we start to think about it more clearly, we can start to have an impact on our built environment and hopefully get better outcomes for us and our kids. Thanks very much.
Thanks, Simon. That's excellent. Showed it in context, I suppose, in terms of the overall impact, but what we really need to do to improve, or why we really need to improve the indoor air quality in our buildings. Our third presenter, Medeina Macenaite, is a doctoral researcher here at the University of Galway, and she's going to give us some insights from the BVent study, which looked at exploring human interaction with ventilation and indoor air quality. So over to you.
Thank you so much. Just to confirm, can you see my slides okay?
Yes.
Okay, so hi everyone, my name is Medeina. I'm a second year PhD student at the University of Galway, and I'm just using my psychology background to look at the human interaction factor with ventilation and indoor air quality. So I'm just going to be presenting on behalf of the BVent research team. And we all know that we design building systems to meet performance metrics, but these systems ultimately operate within a social context with just a home. So today I'm just going to be presenting some data from a survey that illuminates this critical human technology interface and its profound implications for all of us in the built environment. I just want to quickly thank everyone on the team, especially Dr. Marie Coggins, who I'm sure some of you might be familiar with her work and who I'm covering this presentation for. So the building performance gap is a well-known challenge, but a systematic blind spot remains. the occupant. While a process of design, installation, and commissioning is robust, the occupant who ultimately dictates the success of the systems we install into the home is often overlooked. Our research investigates this final component, identifying the key behavioral drivers of indoor air quality and ventilation interaction to provide actionable insights for design, practice, and policy. So overall, we surveyed over 500 people who live in Ireland who occupied energy efficient housings, which we were either retrofitted or new builds, which we classified as built from 2019 onwards, and they must have had lived in the home for at least 1 year, just so they were familiar with all of the seasonal patterns. So notably, 85% of the residents were in social housing, which offers vital insights into the sector. The sample is predominantly located in an urban suburban area, with 2/3 being new builds and mostly having heat pumps as the primary heat generation, and at least had a B2 rating, and which reflects the modern housing stock. So the ventilation data reveals a key insight. Over half of the sample reported natural ventilation as the primary form of ventilation, which highlights the fact that there's widespread occupant confusion, as most of them are living in new builds and they should have had a mechanical ventilation system. Wall vents are common, but trickle vents are rarer, which is most likely due to modern windows, which no longer have trickle vents for the most part. In practice, about 75% of residents have reported frequently ventilating the kitchens and bathrooms during activity, regardless of type of ventilation in those two rooms, as you can see at the bottom of the screen there. So to systematically diagnose behavior in the survey, we were using the COM-B model, which is a health psychology theory, which is a root cause framework to analyze human factors. So the model states that interaction between three components is what actually forms behavior. And these three components are capability, opportunity, and motivation, which are all different colors on the screen there. So capability refers to the physical and psychological means to enact behavior. So that is typically your knowledge levels, your skill levels, your ability to actually do something because you understand it. Your opportunity covers the physical and social external factors which actually enable behavior. So these are things like your social norms and your actual access to technology. And motivation considers these reflective and automatic internal processes which activate and inhibit behavior. So these are more like psychological processes which are in your mind. So reflective stuff involves conscious thought processes such as your beliefs and your goals that influence your decision making. And automatic motivation is driven by your unconscious responses like habits and emotional responses that just happen by instinct. So the COM-B model kind of explains behaviors and interaction between these two components. And most importantly, if we look through the lens of the COM-B models, it tells us exactly where to intervene in order to promote the behavior we want to promote. So for example, in the BVent survey, we were looking at how to actually promote ventilation interaction in the home and knowledge of indoor air quality. So I'm just going to kind of do a walk at example of this model with some data from our survey. So we were looking at people who reported blocking the vents. So either a wall vent or a trickle vent. The sample size is a little bit smaller here because only about 1/5 of people reported vent blocking behavior. So a COM-B analysis kind of follows after statistical quantitative analysis. It's kind of a qualitative view of your analysis. So it's kind of a mixed methods approach. And as you can see here, motivation explains 3/4 of vent blocking behavior, which is the yellow box. So occupants blocked vents to either save the energy and increase the thermal comfort, which is kind of a rational decision based on the goal, which is to save money and be comfortable in the homes. A solution to that would be to actually reframe the values. So for example, that leaving your vents open could prevent mold, which costs thousands and thousands to repair in the long term. Environmental factors like noises or smells were a secondary reason for people to block vents. So placing vents away from your bed or higher occupancy areas could reduce this because you won't actually smell or hear the noises as frequently because you're not near the vents. Our team is inferring that the category of order was predominantly addressing people's lack of understanding for the purpose of vent, so the actual knowledge levels, which falls under capability, which is the red box. And this could be resolved through educational means, such as explaining airflow and the fact that the trickle vents need to be opened so that the air actually flows completely to the house and actually removes the stale air, letting the fresh air in. So the solution isn't just better engineering. We have to reframe ventilation's values in terms of cost savings and health to make not blocking the smarter feeling choice. So overall, the company model kind of explains that you need skills, tools, and values to actually change behavioral. And sometimes one of these components is more important to consider if you're looking at a specific behavior. So for this one, motivation was the primary component of the company model for vent blocking behavior. So our analysis reveals two distinct psychological pathways that drive ventilation behavior. So first, the reliable motivation behavior, which is all about your psychological processes in your brain. So we found a statistically significant moderate positive relationship between valuing air circulation and ventilation in your home. So this is a comfort-driven pathway where people feel stuffy or notice others in the home, and then they're more motivated to act. So they would open a window or use ventilation in the bathroom after a shower. And so people basically essentially feel the bad air and they ventilate, which is kind of a reliable and automatic process because it's to do with internal processes. However, we found the capability pathway is severely compromised, which is to do with your knowledge levels, your ability to act, and your skill set. So we cannot expect knowledge-driven and preventative behavior when 50% of the sample actually start with little to no knowledge. As you can see here, 50% of the sample had either no idea or very vague idea of the concepts of indoor air quality and indoor pollutants. So the statistically significant correlated gap between knowledge of indoor air quality and indoor pollutants suggests that educational interventions could improve mitigation behavior across both domains. And the result from this is that ventilation is primarily a reactive behavior rather than preventative. So people ventilate when they're uncomfortable or they feel the need to, but they can't ventilate preventively because they lack a fundamental knowledge to understand why they should, due to the lack of knowledge of concepts like indoor air quality and indoor pollutants. So we're trying to build these sophisticated ventilation practices on a broken knowledge foundation where half the users don't actually know why they should care about these invisible pollutants that they're breathing in. So more simpler and accessible messaging is needed to bridge this massive knowledge gap. So we also looked at a subsample of people with mechanical ventilation who reported they had mechanical ventilation in the sample. So I'm just going to look through three different types of analysis we did here. So we performed a latent class analysis, which looks as a subgroup division of a sample to see if people fell into the specific groups about how they perceived the benefits of ventilation. So we looked at 5 potential benefits of ventilation. So that was to save money, increase the property value of your home, to save energy, improve health, and provide comfort. And we found a 3-group fit model was the best fitting. So these 3 groups are the comprehensive endorsers, which were about a quarter of the sample, and they basically believe strongly that ventilation would benefit them across all 5 of these components we were looking at. The selected skeptics were about 20% of the sample, and they believe in comfort and health, but they question the economic value of ventilation practices. And the largest group, balanced responders, who were approximately 60% of the sample, were moderately positive across all of these 5 different domains, and they're open to persuasion. If you look at the diagram here in the bottom corner, to improve health and to provide comfort, you can see that the 3 colors go strongly against the 5, which means that all of these groups really did rate as health and comfort as the primary motivators for ventilation practice over the economic values. When we look at what drives the operation of mechanical ventilation in the home, we can see that the comfort and immediate needs dominates. So where occupants choose to use the system to respond to thermal discomfort, similarly to where we saw the vent blocking behavior, and the barriers to operating here mechanical ventilation are systematic, such as the complex controls of these interfaces, the lack of perceived benefits, and practical concerns about the noise and the cost of the systems. And this isn't just user ever is a usability and a communication failure from our end. And most importantly, we also found that there was no statistically significant difference between communication methods for operating mechanical ventilation and perceived helpfulness of these sources. So installer demonstration, social media and online videos all scored similarly well in perceived helpfulness, and which tells us that people don't actually prefer one specific channel of information for MV operation. They need consistent messaging across all of these channels. So the combined implication is clear. We need to tailor messaging to these belief profiles while ensuring consistency across all touch points and communication methods. So for example, focusing on the comfort and health benefits of ventilation over the economic values of ventilation. We're going to now just examine the concerning gap between satisfaction, knowledge, and perceived risk, specifically through the indoor air quality lens for the survey. So this was a Spearman's rank correlation, and our data reveals concerning compliancy and indoor environmental quality. We found strong positive relationships between overall reported satisfaction of your indoor environmental quality and some of its key predictors, which were air quality, odor, and temperature. Occupants perceived indoor environmental quality holistically based on a combination of these interacting factors, while we, from a research academic point, would view all of them as separate components. So solutions cannot target these single metrics in isolation because that's not how occupants perceive them. We must adapt an integrated approach to design and operate that addresses all of these IQ factors simultaneously to genuinely improve the occupant experience and to actually communicate with them in a way that they actually understand from their own lived experiences. Public awareness of invisible pollutants is dangerously low. Awareness of key pollutants like radon, VOCs, and PM2.5 are low, which are the very pollutants that our ventilation systems are actually designed to filter out. These pollutants are quite concerning due to the health impacts. For example, radon is the second cause of lung cancer just below smoking. VOCs are linked to also lung function, irritability in your body, and potentially cognitive dysfunction, and PM is also linked to lung cancer. National awareness programs do actually work, as we can see that there was a very high awareness of carbon monoxide, and there has been a lot of public health campaigns in Ireland specifically to increase the awareness of carbon monoxide poisoning. So we need to integrate similar campaigns, for example, for radon due to its severe health risks and the geographical context of Ireland, where there's very high radon areas across Ireland. We also found that the knowledge levels actually directly influence the risk perception of the occupants. So we got asked them to select which of the pollutants had the highest risk factors to themselves, and we divided them based on knowledge groups. So people in the high knowledge groups were aware of at least 5 out of 7 pollutants we had listed, and they kind of disproportionately identified a huge variety of pollutants with the greatest health risk to themselves, listing things like VOCs, formaldehyde, radon, and PM2.5 as the greatest health risks. Those in low to medium knowledge groups primarily associated health risks with carbon monoxide only. So this satisfaction knowledge gap explains why proactive ventilation is so rare. If people feel comfortable and don't actually understand the invisible risks that they're surrounded with, why would they actually change the behavior? We must make the invisible visible, as Paweł said earlier, and connect comfort to comprehensive air quality, not just the absence of obvious problems like mold and condensation that you can physically see. So in summary, our research reveals that human behavior isn't an external factor, it's an integral system component we've consistently failed to design for. We learned that most problem behaviors, such as vent blocking, are rational responses to the systems we've actually designed. People block vents to save heat, underuse mechanical ventilation systems that they don't actually understand, and they make decisions based on incomplete information due to a very low knowledge level of indoor air quality and indoor pollutants. The implications are clear. We have to design for usability, not just performance, and we have to tailor messaging about these issues to different belief profiles and communicate consistently across all channels. And we have to bridge this massive knowledge gap that prevents the proactive behavior for ventilation and make it not just reactive. Moving forward, we need to stop blaming users and start fixing systems. We have to measure real-world operation in real-life situations, not just laboratory performance of these systems. And we have to integrate behavioral science as a core part of the built environment. Because ultimately, human behavior is not a variable that could be controlled for, but a system they designed for. Thank you so much. Hopefully that didn't overwhelm everyone coming from a behavioral science perspective, and my email there is on the screen if anyone wants to reach out.
Thank you very much, Medeina. That's great. It's great to have see data there from a study, a comprehensive study there on behavior, and the key message there is people react to what they can feel, like the stuffiness, the odor, the humidity. So if they can't feel it, they don't react, and that's partly because they don't have the knowledge in there. So we might touch into that in some of the discussion later on. And I suppose for building professionals, we have a responsibility to make sure that there is good quality indoor air in terms of our design and our delivery of the buildings. Because when we looked at that statistics around there, that of say if someone that lives for 80 years, that typically spends 70 years of their life indoors, and in particular in your home, 55 years in your home. So really, really important why we need to have high quality indoor air in our home. So we'll pick that up in our discussions at the very end. So if anyone has any specific questions or any general questions or comments for our presenters, please do post them in the Q&A function at the bottom of the screen. So we're over to our fourth and final presenter, who's Dr. Eoin King, who is director of the Galway Sound Lab here in University of Galway, and he's going to talk about room acoustics and indoor environmental conditions. Again, so towards these healthier and happier buildings, and the healthier and happier the buildings are, the healthier and happier people that use the buildings are going to be. So over to you, Eoin.
Thanks, Jamie. So you can see my slides and hear me okay?
Yes.
Yeah, great. Okay, so my name is Eoin King. I'm a lecturer here in mechanical engineering at the University of Galway and a director of the Galway Sound Lab. And yeah, I'm going to switch tracks a little and focus more on acoustics rather than air quality. Acoustics and noise and sound, it's often overlooked, but it can have a serious impact on people. And so I'll briefly explain some of those impacts today and what we can do and what kind of work we're doing to address it. So the impact of sound on people and places can have significant effects. Some are listed here. Most notably, it can impact the cognitive impact. So tasks that involve sustained attention and memory recall are often compromised. Studies suggest by about 15% in open plan offices with distractions. Another study has said that if you're in a sustained period of thought, you're working really hard and you get distracted by noise, it can take up to 20 minutes to regain your focus and continue with that, continue where you were. So it can have a significant impact on productivity. In terms of health, we know that noise causes serious health. The World Health Organization estimates about 1 million people are suffering, or 1 million healthy life years. Sorry, 1 million healthy life years are lost every year in Europe due to noise exposure. Oftentimes that's framed in the context of environmental noise, and we talk about it in terms of sleep disturbance, in terms of stress. We talk about road traffic noise, railway noise, aircraft, and so on. But obviously people live in buildings, and that's where people are exposed to that noise, to those noise levels. That's kind of in the home, but in the workplace as well, people are exposed to noise levels, and noise in the workplace can lead to stress, and stress then can lead to cardiovascular effects. Obviously, you're probably all aware that noise-induced hearing loss happens in the workplace, and noise-induced hearing loss is the #1 occupational illness in the world today. Noise in the workplace or inside buildings can impact communications. So one study, we'll talk about it later on, but there are studies that show that dispensing errors in hospitals can come about because of communication errors and because of existing noise or high levels of ambient noise. Essentially, as noise levels go up, errors in dispensing medication can go up as well. And we've talked about how air quality can affect productivity. Noise can affect productivity. The statistics are a little bit more stark. One study in the UK found that productivity can be reduced by about 66% due to people working in an environment where the acoustics are not suitable for those specific tasks. Noise can affect health. It can also affect well-being, reduce stress. And on the flip side, good acoustics can increase well-being and can increase acoustic comfort, and can increase productivity. And obviously, communication can be significantly impacted by acoustics. And then oftentimes noise, or the ambient noise and background noise levels, are the #1 complaint in offices. It's what annoys people the most. And I often think it's because, particularly in hospitals, during surgeries, it's the sound of other people talking that is actually the #1 noise complaint. And oftentimes I think it's because this is all controllable. We can control noise. We know what we need to do, but it's just not being done. So, and I think that's why people can be sometimes more annoyed by noise, because a lot of the times the sources are within someone's control, but nothing is being done. When we talk about noise and we talk about indoor soundscapes or sound, there is a subtle difference, and this is kind of where the science is telling us to go now. In that noise control in the past was always about reducing noise, trying to eliminate noise. But now we know that some sounds are good. And sometimes the goal is not zero noise. Sometimes the goal is a good soundscape that has sounds rather than noise. And those sounds are sounds that people want to hear rather than noise, which are sounds that are out of place or sounds that people don't want to hear. And if you think about this in an open plan office, dead silence might not be what you really want. You might want a little bit of background hum. You might want some sounds to kind of, make it less eerie in an office environment. But it very much depends on the context, and it very much depends on the space you're working within. And there's a variety. There's a whole rake of different spaces that acoustics will vary for. I've divided them up into 3 different kind of broad categories, but there's many more than these 3. But I've divided them up into residential spaces, commercial spaces, and educational spaces. There are many more. But in residences, in people's homes, generally it's all about noise control. Generally, we want to eliminate noise coming from outside into the inside. We want to eliminate noise from room to room, so that the noise from your washing machine isn't impacting the noise in the sitting room. And we want to eliminate noise coming from upstairs going downstairs, so you don't hear footsteps above you in the apartment above you. But it very much is one of stopping sound transmission. We know how to do this. Sometimes it's expensive, but it's never quite as expensive if you do it from the start. So oftentimes the key to good acoustics is to include acoustics in the design process from a really early stage. If we switch into the commercial world, these would be buildings and offices and so on. Here, yes, we do want to reduce the noise, but the goal here is probably not zero noise, and I'll explain why. But ultimately, the first thing we want to do is stop sound transmission. So we want to stop the noise from outside coming inside. And we do want to stop noise transfer from room to room. But we are also concerned about speech privacy. So we need a certain amount of background hum so people can feel like they can have conversations without being overheard or without being heard. So in order to ensure speech privacy, there's a little bit of background noise or background hum is needed. Reverberation time is it's a measure of how long a sound persists in a room. Generally, you want a tight or a low reverberation time, so the sound doesn't persist, for too long. But a certain amount of reverb is actually good. It can improve the sound quality in a space, depending on the context in which it's used. And here in my little box here, I show the background noise can lead to as much as a 66% drop in productivity. So the need to consider the prevailing acoustic environment is now becoming more pressing. And there are more and more studies that show that this is a real cause of concern. And there are now a number of standards that we can work towards. We are guided by science to determine where we need to go. Education is my last kind of broad area that I can consider. Here, we're worried about the ambient or the background noise levels. You can imagine if children in a classroom, if they're living beside a road and the noise from the road is coming into the classroom, that can impair their performance, it can compare their cognitive load, it can compare their listening skills and so on. But equally the reverb time. The reverb time, if your reverberation time is too high, that means words start to blend into each other. So reverb time, a high reverb time is really good for music, but really bad for speech, because syllables and consonants, they tend to blend into one another. In a learning environment, that's not good for children. So we want to control the reverb time, and we want to control background noise in an educational setting. Equally, there's hospital settings, there's entertainment spaces, and they would all have different acoustic or appropriate acoustic conditions. We won't get into them today, but I think most of you can appreciate that it's complex and it depends on the context. Traditionally, we have really focused on noise control. You know, the typical errors or issues that we would commonly come across would be a lack of proper insulation or gaps, holes in walls. So a hole in a wall, sound will always, it's like water, sound will always go to the weakest spot and it'll travel straight through a hole. If there's an air gap in a wall, and that could be a little gap around the window or around a door seal, it's as if the wall is only half as thick as it was, or you know, it's sound can easily transfer through any holes or gaps or anything like that. And sometimes we forget about flanking paths. So flanking is where sound can go around a wall or over a wall or under a wall. So oftentimes in an apartment, you know, a wall might be built to spec, but the sound can go through the floorboards, it can go up through the ceiling and into the room next door. So neglecting to consider those flanking paths is a common error. And then it's really common sense, the idea of a zone approach in planning. This would be when you're planning an apartment block, you don't put someone's bedrooms beside a lift shaft or beside a kitchen. So you design your building so that your noisy sources are together, and your more sensitive rooms like bedrooms are placed away as far away as possible from the noisy spots. In the past, noise control measures were often seen as an afterthought. Thankfully, things are starting to change. You know, and now noise is being considered, acoustics are being considered much earlier in the design process, which is really good, because as I tell my students, it's easier to knock down a wall on paper. All you need is the rubber, just rub it out. Whereas when you build it and you build that wall and you know that wall shouldn't be there, that's a much harder fix. In Ireland, we have the building regulations, Part E, that requires buildings to provide a reasonable resistance to sound transmission, both within and between buildings, between dwellings. So it's looking at that noise from outside to inside, but also inside to inside. And when you look at LEED building certification or WELL building standards, they've started to consider sound. So the WELL building standard is a performance-based certification system that promotes health and well-being. And it includes factors like air quality and light and thermal comfort, but it also includes sound now. So your certificate for your WELL building, you can build upon that certificate if you consider the sound of the space itself. So one thing that I kind of glossed over would be, traditionally noise control is talking about zero noise. Noise is a problem, we must get rid of it. The soundscape approach kind of flips the script a little bit. Instead of looking at noise as a waste product that we have to eliminate, the soundscape approach treats the acoustic environment as a resource, and it's a resource that should be protected or should be controlled in some way, whereby we don't want to eliminate all noise. We don't want to eliminate all sounds. We want to keep some of the sounds that we want and eliminate the sounds that we don't want. So it's a slightly different way of looking at noise. It's a resource that we can use to our benefit rather than just try to control it to zero. Some of the research we're doing here in the University of Galway, this was a Construct Innovate seed fund with myself and Dr. Mohammed, who's in UCD. This was looking at advancing indoor acoustic quality through acoustic metamaterials. So metamaterials are pretty cool. It's a fancy word. Meta just means beyond or transcending. So it's using materials beyond what they're naturally used for. So oftentimes sound, any material that is really hard reflects sound. It doesn't absorb it in any way, okay? So sound just hits a hard surface and reflects and comes back into a room. But we can arrange materials now in certain structures, like in lattices and things like that. we can design materials to absorb sound where they traditionally would not have absorbed it. So this project was looking at metamaterials, and we developed an acoustic switch, or a tunable switch, where we can tune certain materials given an array of lattices to absorb sound at certain frequencies. And this is looking at classroom acoustics. Here at the University of Galway, we've looked at 74 different classrooms. What's presented here is the first 30, but we've since done 44 more classrooms. So 74 classrooms have been assessed, and 70% of classrooms do not meet the Department of Education's recommended reverb time, which means the children in Ireland, their education is being compromised because they're going to class, they're going to school in rooms that do not meet the Department of Education's guidelines. We also looked at the costs it would take to bring those reverb times down to the recommended reverb time. It's looking around €2,000 just in materials, which are really just hanging acoustic panels, which are like hanging a picture really. So about €2,000 would get the majority of those classrooms down to the appropriate level of reverb time. This is a relatively new project. I've just started partnering with the University Hospital Galway. This is in the idea of improving hospital soundscapes. We're hoping that if we can improve the soundscape within a hospital, it can have positive impact on patient outcomes. It can improve staff well-being. It can reduce stress, and it also can improve communication. And we have this idea where we'll monitor the soundscape and develop a dashboard that people can refer to. This is really in its early stages, but it's an exciting area that we're looking forward to getting into. And this is a project ongoing with Sonatus Systems. Sonatus Systems are an Irish-based manufacturer of sound level meters. So we are in partnership with Sonatus at the moment, looking at this very topic, which is assessing indoor soundscapes and assessing their impact on workplace performance. We're using machine learning or machine listening algorithms to categorize sound events. So in an office, we can record the sound, not listen to it, but we can identify what events were there. Were there people talking? Was it construction noise coming in from outside? So we can categorize the sound levels, and then we can determine if that was an appropriate soundscape for that particular workplace. And then we have the standardized project, which is a little bit outside of the scope of today's talk, but it's essentially looking at creating an open access building regulation compliant standardized design details for modern methods of construction. It's a partnership between UCD and Galway. We're looking at structure, fire, moisture resistivity, and so on, including sound. So sound is one of the aspects we're looking at. What impact modern methods of construction can have on the acoustic environment in buildings. I think I'm probably going over, so I might skip through. These are just some tips that we can do to control noise. Number one is avoid air gaps, ensure tight seals and connections, avoid direct transmission paths, and oftentimes some noise is good. This is the idea of the speech privacy. We call it, sometimes we introduce noise into a room specifically for the purpose of creating a good acoustic environment, and sometimes we call it acoustic perfume, which is a nice ring to it. But essentially, acoustic impact should be considered at an earliest design stage. Túsma is Latin Hibra. A good start is half the battle. More information is available on our website, the Galway Sound Lab. We're building up our acoustic testing capabilities in the Sound Lab, but I think I'll leave it there because I think we've only got 5 minutes or so for questions. So thanks, everybody.
Brilliant. Thanks, Eoin. Yeah, and look, again, kind of some similar messages that are coming across. When we measure, we find out that actually we're not performing as well as what we should have. So specifications say one thing, design says one thing, and then actually you go and look at the performance for some of our buildings or some of our elements of the building, and they don't meet those initial specification performance. So really get the design right, get the details right, and then make sure that when we do actually measure afterwards that we are getting those suitable performances in there. So we're going to move over to the Q&A session.